The purpose of this video is to go over a particular type of Markov chain Monte Carlo random walk. That's the Metropolis algorithm. And I want to state at the outset that this is very much an oversimplification. Of what we'll see next week when we use JAGs to implement Bayesian data analysis. I want to begin, however, with a review of a couple things. The first is to think about the wandering politician and how that worked. The politician found out from the governor the population of the proposed island, knew the population of the current island, calculated this ratio. If the ratio was greater than 1, then the politician moved from the current to the proposed. If it was less than 1, they might or might not move. Whether or not they moved was determined probabilistically by calculating this ratio. So let's say they got this ratio is equal to 0.9. Then they take a number line going from 0 to 1. There's the ratio of 0.9. They pick a number at random from a uniform distribution over this range of values. And 90% of the time, the ratio would exceed this random number, and the politician would move. 10% of the time, this ratio would be less than the random number, and the politician would remain on the current island. Next item for review is, here of course is Bayes' theorem. The challenge in practice, particularly when there are many parameters, is determining the marginal probability of the data. But this is a normalizing constant, so we can get rid of it and change this to a proportionality sign. And so what this week is going to do is combine these two ideas in the Metropolis algorithm. So what we have is this idea, population proposed. Well, instead of population proposed, what we're going to use is essentially this thing. So we're going to have the likelihood of the data given the proposed value of theta multiplied by the prior probability of the proposed value of theta. You think about the denominator, it's going to be a reflection of this thing. It's going to be the likelihood of the data given the current value of theta multiplied by the prior probability of the current value of theta. So we're just replicating what happened here with this thing here. To keep the notation simpler, I'm going to refer to the numerator as probability proposed, the denominator as probability current, so we don't have to write in all this stuff. So that's the general approach of what we're going to do. Now I want to go over an example. The particular example I want to use is the example of the Hedonist experiment, where the goal is to determine the posterior distribution of theta, where theta can be thought of either as the probability that a randomly selected person will be right-handed, or equivalently, the proportion of the population that is right-handed. So we're going to get some data. We're going to poll n is equal to 10 people and discover that y is equal to 9 are successes. In other words, they're right-handed. Now we have to evaluate this thing. We'll begin at the bottom with probability of the data conditional upon theta current. Well, we need to provide an initial value for theta current. And I'm going to specify this as being 0.8. Now, I only have to do this once. And in a very simple example like this, it doesn't really matter what value I choose as the initial value of theta current. It's not going to make any difference in the long run. So now what I'm going to do is evaluate this likelihood function. We're dealing with a binary dependent variable, so the likelihood function is going to be a binomial. There's the formula for the binomial distribution. It's a likelihood function, so the data are going to be kept constant at n is equal to 10, y is equal to 9. And then what we're going to do is take this 0.8 value, we're going to plump it in there, and we can evaluate this likelihood function. Alternatively, instead of using the math formula, we could have used the R formula, specify 9 successes in 10 trials, put in 0.8 here. Or alternatively, we can think about it graphically. So this is a likelihood function. I kept y constant at 9, n constant at 10. It would be possible theta value from 0 to 1. So this is our likelihood function. And if you look at 0.8, right there, go over here, come across here. And regardless of which one of these three methods are used, this value here is 0.2684. Now the next step is to obtain the prior probability that the value of 0.8 is the true proportion of the people that are right-handed. So what we're going to use as our prior is that since we've got a likelihood that it's a binomial, we're going to choose a beta distribution because the beta is the conjugate prior to the binomial likelihood, and I'm going to specify A and B parameters of 4 and 2 respectively, because in my immediate family we've got 4 successes for right-handed people and 2 failures to left-handed people. So there's a beta distribution. We can put in 4 there, we can put in 2 there, we put in 0.8 there. Again, alternatively, we could either use the R formula, put in theta there, or this is just a beta 4-2 distribution shown here. And so for 0.8, comes across here, you get the prior probability associated with 0.8 is 2.048. So now we've got this thing and this thing. So we just multiply those two things together, and what we get is this value here, 0.550. So we've got the denominator. Now what we need to do is get the numerator. And to get the numerator, we need theta proposed. Where does theta proposed come from? We're going to get theta proposed is going to come from theta current plus delta theta. And where does delta theta come from? It's going to occur as a random draw from a normal distribution with mean 0 and standard deviation sigma. The choice of this sigma is not trivial, and we'll explore that more in the next week. But for the time being, let's just pretend we got a value of delta theta of minus 0.1, which would give us a theta proposed value of 0.7. So now essentially what we're going to do is we're going to take the process that we used for the denominator with theta current is equal to 0.8 and repeat it for the numerator with theta proposed is equal to 0.7. So again, theta kept constant at 10 and 9. Now we put in 0.7, 0.7 here, 0.7 here. And what we get is, when we evaluate the likelihood functions for 0.7, we get 0.1210. And we repeat that for the prior distribution. Again, a beta 4-2. Now 0.7 goes in here, 0.7 goes in here, 0.7 goes in here, and we get 2.058 for this thing here. We now multiply this guy by this guy, multiply them together to get this. And there it is right there, 0.249. So what is the next step? The next step is we calculate the ratio. We need to calculate this ratio. So we take 0.249, we divide it by the 0.550, and that gives us 0.453. Now we got to decide whether or not to accept the proposed value or retain the current value. So what's the algorithm? The algorithm is that if this ratio is greater than 1, then the proposed is accepted. If it's less than 1, then it's accepted probabilistically. So how do we do this probabilistic possible acceptance of theta proposed? Well, there's our ratio, 0.453, and there's a number line that goes from 0 to 1. So we draw at random a number from a uniform distribution that goes from 0 to 1. And if this ratio is greater than the randomly drawn number, then we accept theta proposed. It becomes the new theta current. Otherwise, if this ratio is less than the randomly drawn number, then we retain theta current. So that's the first iteration. And then we just repeat this process. One way or another, we've got our theta current, so we tally it. Then we create a new theta proposed. It's going to be theta current plus delta theta. Again, we're going to have another random draw from a normal distribution with standard deviation sigma. So we're going to get another delta theta. We're going to get another theta proposed. We repeat that process, and we go over this process 5,000 times. So you have 5,000 iterations. And so we keep track of, we tally the values of theta current, and at the end, what we get is a bar plot that shows the number of counts. This bar plot here shows the number of counts of theta current. There's theta current, number of counts initially on the vertical axis. Then what we do is we divide the height of each one of these bars by 5,000. So this thing is returned to being, or is made into, I should say, a probability distribution. So now we have our posterior probability distribution, which is based on our tallies of theta current divided by 5,000 to give us something that sums up to 1. And what I've done here is superimposed upon it the posterior distribution we got via using conjugate priors. So everything works out really nice. So that's just an example of the Metropolis algorithm in practice. One thing that's really important knowing is that what I've gone over here is really a really big oversimplification of what's going to happen when you actually, or when someone actually does analysis on real data. The whole idea, however, is although this is oversimplified, it's going to be adequate for next week when we look at the runjags package and we use R to calculate the posterior distribution.